So this video is going to contain question number 2 from the 2014 BC exam. And this is a calculator question where they give us these two polar curves. So the first polar curve is just a circle, constant radius of 3. And then the second polar curve is going to be the curve that's traced out right here, defined by this relationship between r and theta. The graph given ranges with theta from 0 to pi, and what we're asked to do in part A is to find the area of this region that's shaded and labeled as capital R. So what I noticed here was if I just look at the piece of this region in the second quadrant, really all this portion of the region is a sector of a circle, where this would be a right angle, right? Theta would go from pi by 2 to pi as we range from this point to this point. But if it's a circle, I don't have to use any real calculus in order to find the area of this portion of R. All I would have to do is use the formula for the area of a sector of a circle, which is 1/2 r squared times whatever the angle that we're considering from that circle is, and we're considering pi by 2 radians of the circle, or 90 degrees of the circle. And so if you simplify that, you get 9 pi by 4. Now the other portion of this region is going to be a little bit trickier to deal with. This region that's obviously not a sector of a circle, the outer edge of this region is defined by this curve right here, which is not a constant radius, so we don't get as lucky and get to develop the answer as quickly as we did over here. But what we want to do in a situation like this, anytime you're finding the area bound by a polar curve, consider a sector of that region. So here is a sector. Now it's not a perfect circular sector because we don't have a constant radius on this little portion of it. But if we think about applying the formula for the area of a sector to just this little almost triangular piece that's drawn right here outward from the origin, it would be 1/2 r squared, and r for this curve is, r for this particular curve is defined to be 3 minus 2 sine of 2 theta. So I'm doing 1/2 r squared, and then what I have right here is my angle is some tiny change in theta. So I'm just going to call that delta theta. Well, what I want to do is I want to add together a bunch of sectors that would sit within this region that have the same area as this one does. And what we can do to add together an infinite number of things is we can use a definite integral as our tool to carry out that process. So we're going to integrate this expression. The delta theta is going to become a d theta. So the only other thing that we would have to tack on here would be the limits of integration, and those limits are going to have to be the angles, right? Our variable of integration here is theta, so it would have to be the values of theta that we range between to trace out this portion of that graph. Well, here is where that graph begins at a theta value of 0, and here is where the circle and this curve intersect, and that happens at a theta value of pi by 2. So if I do that integral from 0 to pi by 2, I'm going to have the area of this figure here that almost kind of looks like a boot, and the total area of R is just going to be the sum of the two. So this is a calculator question, so there's no sense in trying to evaluate this by hand. You're not going to really be able to do that anyhow. It's a function that we can't really find an antiderivative for if you FOILed this out. So we're going to be tossing this into the calculator. So here's my TI-83 input screen here. I did it from the home screen, and I got a value of 9.708 square units for that area. When we move on to part B is asking us for the curve 3 minus 2 sine of 2 theta, find the value of dx d theta at the theta value of pi by 6. So what we need is we need a relationship between x and theta. And if you just take an arbitrary point in the first quadrant here and you draw yourself a little right triangle, the x-coordinate of this point is going to correspond to the leg across the bottom of the triangle. The y-coordinate is going to correspond to the height or the vertical leg of that right triangle. The radius, if we're considering a set of polar coordinates, would correspond to the distance we are from the origin. And then theta in polar coordinates would correspond to this angle that we're opening with from the positive portion of the x-axis. This little right triangle, if you use x over r in the cosine ratio, x over r, adjacent over hypotenuse, is going to have to equal cosine of theta. That means x is going to equal r cosine of theta. You know what r equals on this curve, and so if you put this value in place of r, 3 minus 2 sine of 2 theta, what you have is you have a formula that has x represented as a function of theta. And what you want is you want the derivative of that formula with respect to theta. So you could do this one of two ways. If you want to do it the long way, it would be, okay, I'm doing the derivative with respect to theta. I'm going to have to use a product rule. Within that product rule, I'm going to have to use a little chain rule for the derivative of this term. You can then put pi by 6 in place of all your thetas and evaluate. But if the calculator's in play, take every shortcut that you can. And a graphing calculator has the capability to numerically evaluate a derivative. So I want the derivative of this evaluated at pi by 6. So I toss that expression into my calculator. Watch the grouping symbols. That'd be the one thing to be really, really careful of here if you are utilizing the calculator. Comma, variable of integration, comma, where you want the derivative evaluated, and in this case it was pi by 6, and you get negative 2.366 for that value. When we move on to part C, it says that the distance between these curves changes as theta ranges from 0 to pi by 2. And that should be pretty obvious. Here, the value of the curves would be equivalent, right? The curves are touching. Here, they're touching again. And then as we let theta range from this value to this value, we see that this curve is kind of distancing itself from the circle. So what I wanted to do right away when I saw that I was asked to figure out the rate that the distance between the curves was changing at pi by 3 to figure that out, I wanted a formula that represented the distance between the curves. So I knew that my bigger value, my bigger r value, was going to be the r value on the circle, and my smaller r value is going to be the r value on this curve. And so I said the distance between them is then going to be the r value from the circle minus the r value on the inner curve. And I simplified that. Be careful with the distribution there. And if you cancel your 3's and successfully distribute, you end up with the distance between the curves in the first quadrant being defined to be 2 sine of 2 theta. You want to know the rate that the distance between the curves is changing at this angle. So you need the derivative of this expression, and you need to evaluate that at pi by 3. I took the shortcut of using the calculator again. Right? I could have taken the derivative of this using a chain rule and then tossed pi by 3 into it. I said, well, the calculator's in play. I'm just going to toss this into the calculator. I'm going to evaluate that derivative at pi by 3. And I got an answer that rounds to 3 decimal places to negative 2. If we check out part D of this, it says a particle is moving along that inner curve, and we know that d theta dt is equal to 3 for all times that are positive. We want to find the value of dr dt at theta equals pi by 6. So you've got this relationship between r and theta. If we want to find dr dt, we're going to take the derivative of both sides of this equation with respect to t. So the derivative on the left is pretty easy. We get dr dt. The derivative on the right is the piece of this you have to watch out for. Theta changes over time. The rate of change of theta with respect to time is 3. And so when we do the derivative of this side with respect to t, what we're actually going to have to do is we're going to have to use a little chain rule and differentiate implicitly. So the derivative of 3 is 0, and then I copied my negative 2. Derivative of sine is cosine. I left my inner function inside that cosine ratio, and then I'm multiplying by the derivative of this inner function. Well, the 2 is a constant, so I'm copying this 2, and then the derivative of theta with respect to t is going to be d theta dt. And then if we put pi by 6 in place of our theta, put the value they gave us for d theta dt in place of d theta dt, and evaluate, you get a result of negative 6.